matter, but always make sure that I am recording, because somehow, even though I thought I was recording on Friday, I did not record. And therefore, I was unable to post the Zoom lecture from Friday. But I am trying to remember to. It's just not common for me to do so. Any questions, any comments, always ask. Okay. So let's go back to College Chemistry 1 temporarily. A solution consists of a solute and a solvent. The solute is typically, when I say typically, it's almost always the minor component. Whereas the solvent is the major component. Oftentimes, the solute is going to be the substance that changes state of matter. But that is not always the case. So you can't use that definition. So that's why we use the definitions we do. Let me, number one, make this black ink so it'll appear better. And number two, I will write larger. I sometimes forget, so. Okay. Now, thus far in your experience, the majority of solutions have been a solid that has been dissolved in water. But a solution does not have to simply be a solid dissolved in a liquid. An example of this is the air you breathe. You have the solute is a gas, oxygen, carbon dioxide, argon, other gases that are dissolved in a gas, which is nitrogen. The two together make a gaseous solution. Now, we can have a gas that is dissolved in a liquid. Drinks, carbonated beverages are an example of this. You have carbon dioxide that has been dissolved to make the carbonate in the carbonated beverages. And ultimately, what you observe is something that is a liquid. As previously stated, yes, we can have a solid that is dissolved in a liquid, such as salt water. And we can have a liquid dissolved in a liquid. A common example of a liquid dissolved in a liquid is 70% isopropyl alcohol. Isopropyl alcohol is a liquid and it is dissolved in water, which is also a liquid. All of those would give a liquid as the solution phase. Now, you also can have a solid dissolved in a solid to make a solid solution. An example is brass, where you have copper and zinc combined. Depending upon how much copper depends upon how yellow the brass is. So solutions are more than what we have typically dealt with in our class thus far. They really are all it means is that you have a solute dissolved in some sort of solvent. Typically, whatever that solvent phase is, that is what the solution phase is. Now, admittedly, in our classes, we typically deal with, and by the way, I don't know if everybody uses this, but you'll see me shorthand solution as SOLN. And I just don't know who all uses it, so I'm going to preface that. I use SOLN as solution. But anyhow, most of ours is an aqueous solution, so the solvent is water. And the solute can be gas, such as hydrochloric acid. It can be a solid, such as copper sulfate solution, or it can be a liquid, as I've already given you. The most common example is isopropyl alcohol. Now, here's where we get into things. Basically, if you'll remember from college chemistry 1, you had a solubility table. No, I'm not going to make you remember the solubility table. If you need it, I give it to you. But what does the solubility table basically say? It basically indicates that not all solvents or not all solutes will dissolve equally in a given solvent. While sodium chloride dissolves in water, lead chloride or lead 2 chloride does not. To any appreciable amount. Grease does not dissolve in water. That's why we add a soap to it, in order to get the grease and the water to combine. So not everything dissolves equally in a given solvent. Solubility describes the degree to which a solute dissolves in a given solvent. We're going to work with the solubility of various ionic compounds in water on Friday. We'll talk about factors that affect solubility, and we'll get into this concept of solubility to a greater extent at that point. But you've already been exposed to it, so it's a matter of just remembering what it all means, hopefully. Now, so the solubility table was but one example where a solute does not dissolve in a given solvent to any appreciable amount. So let's look at the qualitative determination of solution formation. Basically, when we get into the qualitative determination of solution formation, the key to remember is like dissolves like. What this means is a polar solute is more likely to dissolve in a polar solvent. And nonpolar solutes want nonpolar solvents. So let's look at structure. So this again comes back down to structures and intermolecular forces. Let's take an ion dipole force. We have sodium chloride. Sodium chloride consists of a positively charged cation and a negatively charged anion. It is a substance that has a constant positive and a constant negative. Sodium chloride is going to dissolve in water because water also has a constant positive and a constant negative called a partial dipole, where you have the partial negative towards the oxygen and the partial positive towards the hydrogens. The positive end of the hydrogen forms an ion dipole interaction with the negative end of the sodium chloride. We would also have an interaction between the oxygen and the sodium ion in another sodium chloride. And we could continue. This type of interaction is called an ion dipole interaction. because you have an ion from an ionic compound reacting with a polarized molecule. Now, I did say polar solute is more likely to dissolve in a polar solvent. Again, lead 2 chloride, although it's got a positive cation of lead 2 plus, and it has 2 anions of chloride minus, they do not dissolve in water to any appreciable amount until you get to much higher temperatures. So that's why I put that likely in there, is just in case you have something that is insoluble. We can also have hydrogen bonding. Between the solute and the solvent. An example, let's use water again, because water is really, it's considered a universal solvent because it does dissolve so many things. Again, you have your partial negative, and that's supposed to be a delta. And your partial positive on your dipole moment. Now, the negative end where did it go? Of the dipole moment associated with the water molecule, that it's being stubborn today, that can hydrogen bond with the hydrogen associated with, say, an ammonia molecule. Which is also polarized towards the nitrogen. The nitrogen could then, in turn, hydrogen bond as well to another hydrogen in another polarized water. And we could continue and continue and continue. Yes.
How are you drawing the water? Like, what are the dashes on the top?
Okay. I'm glad you asked, because it is a notation. So water is based off of the tetrahedral structure because it has 4 groups attached to the central atom, two sets of lone pairs and 2 bonds. So that's a total of 4 groups, 2 lone pairs, 2 bonds. Now, if we think about a tetrahedron, it's basically a pyramid that has 4 sides. But this structure is very difficult to illustrate on a 2D shape. So we use these dashed wedges to indicate that the bond goes behind the plane, or away from you. We use a darkened in wedge to indicate that the bond comes towards you out of the plane. And technically, we use just a straight line to indicate that the bond is in the plane. This is a notation that you do need to get used to because you're going to use it. I'm going to use it a lot during this class, but you're also going to see it in organic chemistry. So basically, if I represent my head represents the central atom. For oxygen, there's a lone pair up here. There's a lone pair over here in the plane. So one up and one down. But it also is going to have a bond that comes to you. So that would be the darkened in wedge, and a bond that goes away from you. So that's the dashed wedge. So that's a way we can illustrate a 3D structure in a 2D plane. Does that answer your question sufficiently? Yes.
How does the hydrogen bond and ion dipole relate back to the solution?
Okay, so basically, this comes back to polar likes polar. We have been talking about polar really with covalent molecules. But if you think about it, when you have an ionic compound, you have the extreme version of polarity because you got a positive and you got a negative. So it's the extreme version of polarity. Whereas when we talk about water, it's the less extreme version of polarity because the electrons are shared, but they're shared unevenly. Does that answer your question?
Yeah, I guess I'm just confused on like how it relates to the ion dipole bond. Like, is it something like we're gonna look at a solution and determine like how well?
If it's the key is if it's an ionic compound dissolved in water, if it's an ionic compound dissolved in a polar compound, it's going to be an ion dipole solution. So as long as there's an ionic compound, and that's because in ionic compounds you have cations and anions. So you have the ions. Okay. Now, you can also have simply dipole-dipole interactions. Example, methyl ether or dimethyl ether, I should say, is a lot like water. It does have a permanent positive and a permanent negative because it is a polarized molecule. It's supposed to be a positive. We can take and interact that with formaldehyde. And no, I don't expect you to know the names, which also is a polarized molecule. And just like before, the negative of one polarized molecule would interact with the positive of another polarized molecule. So you can have interactions between dipole-dipole. Now let's just break this down. Ion or ionic compound, polar, mixed with water, polar. You can have hydrogen bonding because both of the molecules are polar. You can have dipole-dipole interaction because both of the molecules are polar. You could have dipole hydrogen bonding because both of the molecules are polar. Polar wants polar. So the best solvent for an ionic compound or a polar molecule is going to be something that is polar. That's what it boils down to. I'm just showing you why with all of this drawing. Because the positive has to interact with the negative. Polar wants polar because they have a positive and a negative. Questions? Yes.
I don't understand why the dipole is different from hydrogen bond, especially with this scenario where it's the hydrogen and oxygen.
Okay. Technically, that is a hydrogen bond. The reason I called it dipole-dipole is because this is a dipole, this has a dipole-dipole, this has a dipole-dipole. But technically, yes, this interaction is a type of hydrogen bonding.
So the hydrogen bonding example, would those be dipole-dipole as well, or just
I mean, hydrogen bonding has dipole-dipole, so yes, they can be considered dipole-dipole. Basically, it just comes, the key to it is, the main key, polar molecule takes a polar solvent. I'm not going to ask you to draw it. I'm not going to ask you to identify the interaction. I'm asking you to recognize polar wants polar, nonpolar wants nonpolar. So on the optional homework that is available, polar wants polar, nonpolar wants nonpolar. That's the entire nugget. And yes, I could have just said it, but I wanted to show you the interactions and why they occur. Other questions? Okay. So that is the qualitative story. That's the qualitative story. Now let's talk about the quantitative. Quantitative. The quantitative story comes down to two factors. The first factor is enthalpy. The second factor, which we will discuss a lot more later on, is entropy. So let's talk about enthalpy. If you'll recall, the enthalpy is the heat of reaction or the heat associated. With the process. If you have an enthalpy is represented by a delta H. if you have a positive delta H, it means that heat is added. It also means that it is endothermic. And for a solution, it is the energy that must be added to separate solute and solvent molecules. Now, just a reminder, a negative delta H means that heat is generated as a part of the process, as a part of the reaction. It means that it is exothermic. In regard to a solution, energy will be given off or generated when the solute combines with the solvent. Now, the difference in the energy added to separate the molecules and the energy given off when the solution is formed determines whether the solution is exothermic or endothermic. So let's just look at this in a diagram. So it takes energy to be added. So a positive delta H to separate the solvent molecules. You also must add energy to separate the solute molecules. Once you've separated the solute and the solvent, now the solute can combine with the solvent. And it does so, we'll call that delta H mix. And it gives off energy when they combine. Now, if the difference between these two is an overall negative enthalpy, then the overall process is exothermic. Now, no matter what, to separate the solvent molecules, it is going to take energy. To separate the solute molecules, it is going to take energy. But the other option is that when the two combine to form the solution, what you have is you have an overall positive delta H, in which case it's endothermic. An exothermic solution is very likely going to occur. If you have an exothermic solution, the formation of a solution is likely to occur. It is when you have the endothermic situation that the solution may or may not occur. So basically what it boils down to is if the solute solvent interaction is greater than the solvent plus the solute interactions, a solution will form. Also, if the solute solvent interaction is equal to the solvent plus solute, then a solution will form. It's only when the solute solvent is less than the solvent plus solute that the reaction may or may not form. So the question is, so basically what we have is this, how does it form? It may or may not form. From a energy perspective, which energy drives everything. Energy is the currency to chemical reactions. Energy drives everything. Why may it form? from this perspective, if energy is not favorable. Well, again, this talks about the enthalpy. But if you'll look back, I said there were two parts to this story. The second part to this story is the entropy. And entropy is also a form of energy. It is the energy associated with randomness. And the greater the randomness, the greater the entropy. From a perspective of from the perspective of state of matter, the least random type of state is going to be that of a solid. That's because every single one of the molecules are fairly well organized. As we go through this, the next thing in line is going to be that of a liquid. Because we have greater disorder, greater randomness of the molecules. They're not necessarily as clean and pretty. They're just over there. After that is a solution. Because now, a lot of times, especially if we're talking about an aqueous solution, yes, we have this randomness, but now some of those are ions or some of those are another molecule. It's not always the same molecule in there. Finally, we have the gas, and that is the gas is the most randomized substance out there. So when we make a solution, making a solution is entropy favored in most cases because you have a greater amount of disorder. And that greater amount of disorder can be the driving factor behind the formation of a solution that, from an enthalpy standpoint, shouldn't occur. Now, we're not actually going to deal with the mathematics associated with this concept until we get to, like chapter 18 or 19. That's when we actually get into the mathematics associated with entropy and enthalpy. So the big takeaway from that last part is that enthalpy is going to be a huge driving factor. A solvent-solute interaction, if it's stronger than the solute-solute plus the solvent-solvent by themselves, then a solution is going to form. If it is equal, then a solution is going to form. But if the solute-solvent interaction is less than the solute-solute plus the solvent-solvent, then entropy may be the driving factor to make it occur. Questions for me? Not, I'm out of time. And I will see you on Friday for factors affecting solubility. Today, let me think. I will be in my office until around 3:30, but I've got a time here and after this is